Hi, everyone. We're the Ramblin Wrecks team, and our Capstone project is the Modular Impact and Deformation Fan Testing for Tectonic Industries, or TTI. Here are our team members, Tyra, Derek, Philip, George, Katie, Melissa, and Gaurav. For this presentation, we will be going over the following agenda, beginning with our problem statement, then jumping into the original concept, our ideation process, the current concept, including calculations, CAD modeling, prototyping, and coding, and finally, the additional documents and procedures such as the bill of materials. The foundation of our project revolves around developing a batch testing procedure and rig for the impact testing of axial fans. The intent was to be repeatable, precise, and produce quantifiable data that can compare each manufacturing run of fans. However, as the project has progressed and the design has come to fruition, the scope has expanded slightly to a more generalized testing in two specific criteria. The TTI initial concept rig, very rudimentary and inaccurate, resulting in incomparable data sets that do not properly measure the strength and durability of the fan blades. We use the initial concept to determine the most important features to implement, such as impact point, failure criteria, and strike angle on each blade. The initial fixture is based on a testing method known as IZOD, which uses mass dropping to create an impact force on a test subject that is automated and repeatable. Our concept also uses this methodology as inspiration due to the desired testing strategy on fan blades. On this slide is the current concept for the fixture in a simplified diagram and a full rendered CAD model. In the next slides, we will go to the individual subsystems and show the designs and calculations for each. Shown here are the function tree and morphological chart for the subfunction concepts. The four main functions of the fixture are to grip the fan, target the correct blade, damage the blade, and evaluate the damage. To achieve these functions, the group brainstormed many possible solutions and concepts. Then upon further conception and ideation, the solutions in red were shown to be the most efficient. In order to improve the current design, we wanted to implement an empirical testing methodology that accommodates brittle and ductile fans. The ductile fans will undergo deformation at progressive loads, and the displacement will be measured. Meanwhile, the brittle fans will also undergo an impact test, where the energy taken to break the fan blade will be measured. As a part of the iterative pass-fail criteria, this testing will allow us to identify and establish a reference that we can use to compare to fans of the same batch and then later to fans of other batches. Thus, a numerical comparison on the manufacturing quality of the fan blades. If the fans start performing better, the numerical pass-fail criteria could be set to a greater standard. At the bottom, from left to right, is the damage that was observed from rudimentary impact testing prototyping. Sizing the mast cart and drop tower height are critical first steps to the design process. In order to estimate impact forces, a set of example impact times for a variety of materials was obtained and applied to find the mass to induce failure in several modes where bending was dominating. In the top right is a plot that summarizes the maximum mass to induce bending failure at 0.5 meters of height. The plot at the bottom left illustrates impact times as well as a representative impulse force for each. Our maximum energy calculation turned out to be within 30% of the TTI estimate, which is strongly dependent on rig stiffness and impact time. The force analysis for each part is done by breaking down the force components of the impact. The goal is to apply forcing to the blade orthogonally to and at the center of the fan blade. This allows the best transfer of energy to the fan blade and prevents us from having to deal with the associated jacking when impacted at an angle. The fan blade routes, where failure is expected, were simplified as cantilever beams, making the math straightforward.
Here you can see the setup, calculations, and load set that the main fan axle will experience during testing. You can see highlighted above the forces that the shaft will have translated into it by the fan impact, and how those forces propagate into loads at different locations. One of the primary concerns is that the protection of the stepper motor and gearbox. A worm gear was selected for this reason, as backdriving is prevented in a worm gear, thus protecting the motor fully from backdriving torques. Additionally, the bearing in the center accounts for all translational motion in the system, which also serves the purpose of shortening the distance between the fixed point and the end of the beam where the force is being applied. The rotary table and fixture frame to hold the toggle clamp, bearing puck, and gearbox stepper motor component were chosen to provide a large range of angles to place the fans and achieve orthogonal impact points on the blades while maintaining a stiff base for the main axle. The cone holding the fan in place from the top is designed to make the fan coaxial and provide additional support, keeping the fan from popping off the mechanism by bouncing. It has been designed to spin freely with the fan, only providing axial forces, and fit every fan type that is available currently by TTI. The design for the live axle rod encapsulated the need for threading to attach the toggle clamp, an insert tip for connection to the roller bearing inside the cone, and a shoulder to reduce the risk of slippage on the bearing. Once the general design was settled, the machine design calculations were done to verify the strength of the design for both the rod and the cone itself, as well as the bearing within. This was successful, and the cone and clamp design were deemed more than sufficient. On the other side of the fan, the primary rotational clamp was designed to be simple, as the fans have a wide range of radii, rib numbers, and shape, and a standard chuck was impossible to design to account for every fan type. Instead, ethylene vinyl acetate, or EVA foam, was chosen. However, upon assembling and testing the prototype, the foam failed as the fan ribbing sliced through the piece when the cone and toggle clamp applied axial force to the main axle. As a simple alternative, a piece of hardwood was utilized, but that failed as well. After some more testing and brainstorming, the group settled on a large circular disc with a thin sheet of sandpaper adhered to provide the necessary friction while maintaining universal fit that the EVA foam was initially designed for. The main axle of the fan is a simple variable radius shaft that reduces the risk of bending while simultaneously fitting into the hole in the bottom of the fan and connecting seamlessly to the gearbox shaft. The machine design calculations shown here give us the limit of the length of the axle, 58 inches, which is 2 magnitudes longer than what we have made it to be. At this length, the material can withstand the impact force delivered by testing. The bearing and pillow block below the fan and attached to the main axle were designed to eliminate the axial loading on the gearbox as much as possible while still allowing full rotation for indexing function, while at the same time eliminating translational forces that would normally damage the gearbox. The shaft is held in place by a press fit, while the bearing's retention to the pillow block can be adjusted and required copper shims during prototyping due to the hole saw kerf. The gearbox and stepper motor came together as a single unit. They were chosen for the size, precision, price, and gear type. The NEMA 17 motor and the 17:1 gear will, in tandem, prevent the backdriving of the motor and protect the motor from damage. However, upon obtaining the gearbox motor component, it became difficult to mount as the gear was placed directly in line with one of the mounting bolt holes. Additionally, while the motor is de-energized, the motor can be back-driven slightly, so it must remain powered at all times during testing. As the ordered parts came in and the prototype was assembled, many parts, such as the linear XY table, required additional measurements, disassembly, and rebuilding in order to be functional. The linear table did not have a pre-made CAD model available from the manufacturer and required manual modeling to complete the rest of the assembly as accurately as possible and ensure there were no conflicts of geometry. Then, to function adequately, a full rebuild and refurbishment of the XY table was done, fixing many of the parts not adequately constructed by the manufacturer. The fan clamp, in practice, was very effective, but could use a few modifications, such as securing the washers to the clamp arm and also tack welding the bottom nut for ease of use. The XY table performed its job, but was not very smooth and requires manually tightening the jibs to prevent backlash from affecting results. The linear rail and mast cart were designed to be as light as possible using 80-20 extruded aluminum and a simple threaded rod to hold calibrated mast blades. For prototyping purposes, the mast cart was 3D printed and bolted to the linear rail sleeve bearing. It was designed to be a T-beam structure due to the superior performance in bending, shear, and compression, and despite it being 3D printed, this allowed it to survive testing process. The mast cart system is triggered by a solenoid. It is designed so that it can be mounted at different heights, allowing tests to be performed at different amounts of energy.
The firing pin was designed to withstand multiple high-impact forces and compression between the mast cart and the fan blades while delivering the most force and precision to the blades without bending. The design includes a compression spring that acts as a reset and allows the firing pin to automatically start at a higher point and return to that point after impact, which is nestled between the head of the pin and the plastic spacer to prevent overcompression. Using SolidWorks, we were able to determine that the firing pin would clear the puck and allow any broken blades to drop. However, this was done using an old design of EVA foam, so the blades do not drop over as much in the physical prototype. Regardless, this analysis is still useful in determining the firing pin location over the puck. Because the firing pin is on aluminum cantilever beams supported by corner brackets, the bolts that will be receiving the most shear force require machine design calculations to ensure they will withstand multiple high-impact forces. Additionally, the force on the cantilever will create a moment, thus the 3 bolts will not endure the same stress concentration, which was reflected by the calculations. After the physical prototype was machined and assembled, TTI asked us to ensure that the fixture could break through the fan blades. Here's a short slow-motion video of the impact of the mast cart on the firing pin, which caused the fan blade to snap at the root as expected. During the redesign of the fan grip from the underside, the new, larger grip plate slightly interferes with the fan blade as it breaks, which essentially creates a ramp that causes the firing pin to slide down at an angle. The electrical housing box for the fan indexing is a freestanding box that connects all elements of the circuit while still allowing the operator to move the buttons to any desired location around the fixture. The controls include 3 push buttons which allow for direct user interface and an emergency stop button. The push buttons will, for example, index the blade forward one, backward one, or confirm the selection. This is a simplified wiring diagram that will be included with the project when handed off to the sponsor for troubleshooting and updating purposes. The power supply is a 120 volt AC supply that is converted to a 12 volt DC supply. The circuit reduces the voltage using a combination of resistors and uses indexing buttons to control the solenoid and also activate the motor to index the fan blade with accuracy based on the input value and the number of fan blades. Here you can see a simplified overview of the workflow for using the fixture, including the fan blade, number input, angle, tilt degrees, and offset from drop point. These instructions will allow the operator to keep consistent and precise data over the range of fans being tested in each batch. The software flow shown here describes the coding procedure of the fixture that will allow the electronics to automate the process of testing with more precision and accuracy. The code was designed to be simple and straightforward to operate and allow for rapid indexing between fan blades. However, during our testing, the gearbox proved to be insufficient tolerances between the gears and allowed for substantial backlash, even when the motor did not turn at all. For this reason, a different one will be recommended for use rather than the one used for prototyping. Additionally, the galling of the firing pin in the sleeve bearing caused more difficulty in rotation than was expected, so it will be replaced with a plastic one. The deformation test turned out to be highly sensitive to friction in the sleeve bearing and indicates that the bearing material should be changed. It's recommended that an indicator flat be designed into the carriage for easier measurement setup. In practice, the flex arm was convenient and did its job very, very well. The bill of materials for the full fixture can be seen here, not including the materials that were used solely for the prototyping model. The total cost of the product will be about $868. Thank you so much for your time, and we will now take questions.